Problem 4. This is going to be a good example of how we use similarity in the real world. In this problem, our class is making a rectangular poster for a rally, and the poster's design is 6 inches high and 10 inches wide. And we want to make an enlargement of that poster, and that is going to be 4 feet high and 8 feet wide. Now the first thing I'm going to do here is match up my units so that everything is easier. So 4 feet turns into 48 inches, and 8 feet times 12 is 96 inches. And we need to see how this poster is going to enlarge. So if we look here at what has been done, we take 48 and divide by 6. That's our ratio, right? Our heights are going to be proportional. So a 48 to 6 inch ratio, 48 divided by 6, is 8. And if we look at our width, we know that we want 10 to turn into 96. So 96 divided by 10 is 9.6. What we have done here is find out how much we are multiplying by, or how many times does 6 go into 48. And so this is our multiplication factor. Well, we can increase the height 8 times, we can increase the width 10 times. So we are going to have to go with 8. This is our limiting value because it's the smallest one. If we increased the 6 inches by 9.6, it would be too big to fit. So our design can be enlarged at most 8 times. Now we could also have looked at this. 6 times what equals 48, and we would get a multiplication factor of 8. And we could look at 10 times what equals 96, and we would get a 9.6 multiplication factor, like we were doing in 7.1. So there's a couple of different ways to look at this. But we are interested in our limiting value here. We can increase this poster at most by a factor of 8. So we want to use our height here to write our proportion. We know that we are going to use a 6 to 48 proportion. So now we need to decide how big is the width going to get. So we use our proportion on the left side, and we write our fraction bar. Just write that. We always start these. Fraction bar equals fraction bar. And we know that we want to use 6 to 48. And then we say, well, 10, that's not a 10. We know that 10 needs to turn into some value. So we simply do cross multiply, and we get our height is going to be 80 inches. Right? And that should not be a surprise because 10 times 8 is 80. So the largest poster that we can make is 48 by 80 inches. So that means now it's your turn. Go ahead and pause the video and try the next problem. We were asked to use the same poster design in the previous problem, only this time we want it to fit a space that is 3 feet by 4 feet. So that is 36 inches by 48 inches, and I could either do 36 divided by 6 is 6, or 6 times what is 36, and I get a multiplication factor of 6. I can increase it 6 times. The width is 48 divided by 10, gives me 48. 10y equals 48, or our multiplication factor is 4.8. Remember, we have to go with our smallest one, because if you go too big, the other side won't fit. So our width is our limiting value, and we are multiplying by 4.8. So we can write a proportion. We use our width. We're at our fraction bar equals fraction bar and use our width. 10 is to 48, as 6 is to our new height. And we just cross multiply, and our new height is 28.8 inches. We also could have simply done 6 times 4.8, because that's our multiplication factor here. We are multiplying both of them by 4.8, and we would still get 28.8 inches. So a couple of ways to do it. Once again, proportions are one of the most useful things that math has to offer us. So very exciting, very useful. Our final idea here are scale drawings. In a scale drawing, and this is definitely good stuff, your lengths are proportional to actual lengths. Your scale compares the drawing to the actual length. So in a scale drawing, and if you build model cars or in social studies, when you look at a map, okay, there's lots of scales out there. Scale equals your drawing or your model over actual. And this is worth boxing and putting in red. So we are given a scale drawing of the Golden Gate Bridge. The distance between the two towers is the main span. So we are looking from here to here. And we are told that the length of the main span on our drawing is 6.4 centimeters. And we are also given, with all good maps and drawings, a scale. So how are we going to find out what's the length of this span in real life? We simply set up a proportion, and the drawing goes on top and the actual goes on the bottom. So what do we know? We know 1 centimeter is to 200 meters. And then I come over to my other side, and I know that 6.4 centimeters is going to equal X meters, because my units have to match top and bottom. And then we just cross multiply, and we get the length of the span is 1,280 meters. So we get X equals 1,280 meters in real life. Just cross multiplied. Now, the next problem asks you to find the height of the towers. I am going to tell you above the roadway that this is 0.9 centimeters on the drawing. So it's your turn. Go ahead and work this last problem. Okay, these problems were kind of fun. We wanted to find the height of the towers above the roadway. So I drew my fraction bar equals fraction bar, and then I put in my scale, 1 centimeter to 200 meters. No, my drawing is on top, my actual is on the bottom. And then I know my drawing is 0.9 centimeters over some unknown meters. Notice on these we have not changed our units to match each other. This is a legal move. Putting units on these will help you remember, because what we are doing in a scale drawing here is comparing centimeters to meters. 1 centimeter is 200 meters. So 0.9 centimeters compares to my unknown meters. I cross multiply, and then when I find my y value, I know that my answer is in meters. So I get 180 meters above the road. Those are tall. That's really, really tall. And then the last problem here is on the Space Needle in Seattle. We know it's 605 feet tall, and you want to make a scale drawing on an 8.5 by 11 sheet of paper. And you decide to use the scale of 1 inch equals 50 feet. So I know my scale is 1 inch to every 50 feet. The 1 inch is the drawing, the 50 feet is the actual. So this is going to let me write a proportion. I write fraction bar equals fraction bar. I put in my scale, right? My scale here, 1 inch to 50 feet. And then I want to know what it's going to look like on scale because I know the actual. So the actual goes on the bottom, 605, cross multiply, do the math. That means my drawing is going to be 12.1 inches high. This is too big to fit on a piece of paper, so we need to choose a better scale. Maybe go down to 1 to 45, 1 to 40. Okay, so proportions, I just cannot even express how useful and important proportions are. It's best to start out, label your figures, figure 1 and figure 2, or drawing and actual if we're doing scale drawings, and write your proportion, fraction bar equals fraction bar, and then start filling in, making sure that if figure 1 is on top, figure 1 has to be on top. Figure 2 is on the bottom, figure 2 has to be on the bottom. And especially with scale drawings, using your units is important. So similar figures have congruent angles and proportional sides. And what we're really interested in is that scale factor, the ratio of those sides. So if you are careful and show your work, I truly believe that this homework will be very easy for you. So enjoy.